Special relativity has some very, very cool implications to how we observe space and time when things are moving relative to us. It all hinges on Einstein's work. The proof is rather simple. We're not going to get into the proof, but it hinges on Einstein's work that traveling through space sort of steals away some of your motion through time, and the fact that the speed of light having to be constant for all observers. I couldn't figure out how to type it correctly, so I just wrote the word gamma. But the simple proof that I'm not showing, but I'll maybe post it another time, is the correction factor for when we observe moving things, this gamma. It's a Pythagorean theorem thing, so it's got a great big square root, 1 minus v squared over c squared, where v is the speed of the object you're observing, and c is the speed of light in a vacuum. As good as that one is, I find it a little bit easier to work with if I write it a little bit differently and think of it as v over c and then square them both. For the one I made up here, I just made up some numbers. Let's pretend we've got a spaceship going 2 times 10 to the 8 meters per second. When it's not moving, if you were to stand and measure it, it's 25 meters long and has a mass of 10,000 kilograms. Based off the given speed, we can calculate the gamma, and then we'll figure out what that gamma means in terms of the length, the mass, and how time is passing on the moving ship. As crazy as this gamma equation looks, you can do a lot of this in your head as we crunch out the math, especially if I give you a nice clean number like the one we've got. Gamma is going to be 1 over, then we've got 1 minus, the given speed is 2 times 10 to the 8. We're going to divide that by 3 times 10 to the 8, the speed of light in a vacuum. This whole part we're going to have to square, and then this 1 minus part is all under the square root. I like writing it this way because I can see that the 2 times 10 to the 8s are going to cancel. So really, on the denominator, we've got 1 minus 2 over 3 all squared. 2 squared is 4, 3 squared is 9, so really we've got 4 over 9, 1 minus that. I can do that part in my head. 1 minus 4 over 9 is really 9 over 9 minus 4 over 9, so that's 5 over 9, all under the square root sign. I can do a little bit more. 1 over a fraction means we can flip the whole thing over, so it's really the square root of 9 over 5. The square root of 9 is 3. The square root of 5 is going to be some irrational number. That last part, now I'd get out my calculator, and we get that the gamma is 1.34, give or take. If the spaceship had a regular sort of observed length of 25 meters when it's not moving, what Einstein and the constant speed of light kind of come up with, that length is going to decrease by the factor of gamma. In this case, 134. So if our spaceship was 25 meters long, the observed length is now 1.34 times shorter. So as this thing zips by, it's going to look like it's only 18.6 meters long. It's going to be shrunk from front to back. Mass increases by the same factor. So if it standing still had a mass of 10,000 kilograms, when it's moving, it's going to behave like it's 1.34 times heavier, times more massive. So instead of behaving like it's 10,000 kilograms, it's going to behave like it's 13,000 kilograms, 13,400. Really what this means, it doesn't pick up any extra kilograms. What it means is in F net equals ma, since it's behaving like it's a little bit heavier, it's going to take a larger force to get it to accelerate the same way. Or since it's behaving like it's heavier, it's not going to accelerate as big if we push it the same way. So really it's just behaving differently. F net equals ma still works, but it's behaving as if it has more mass than it actually did. The other cool thing about special relativity is time dilates. So we have to think about our perspective. If we're looking at the spaceship, clocks in the spaceship, they're going to be ticking slower by a factor of 1.34. So if, let's say, 1 hour goes by outside the spaceship, so us standing still on the planet, 1 hour ticks by for us. Then if we divide that out, 1 hour divided by 1.34, that's roughly 0.75. Oops, that's roughly 0.75 hours, which is roughly, well, not roughly, which is 45 minutes. So if we stood by outside and an hour went by on our clock, only 45 minutes would go by inside the spaceship. Time has been dilated for those. So the bottom line is, oops, see if we can see more of it. The bottom line is from the speed, we can get the gamma factor. That was this little bit of math. And then we interpret what that gamma factor does. Lengths, the apparent lengths are going to decrease by that factor. It's going to behave as if it's heavier by that same factor. And inside the moving object, time's going to slow down by that same factor.